Hi to everyone and welcome to this Kaeser Compressors webinar. Okay, right now I'd like to introduce today's presenter, Neil Mehltretter. Neil is a certified energy manager and he's the engineering manager at Kaeser. Neil has conducted and overseen thousands of industrial compressed air studies and helped users achieve significant energy savings and operational improvements. He has authored several nationally published articles on compressed air systems optimization and is a frequent presenter on energy efficient systems design. Now, in addition to his bachelor's degree in chemical engineering from the University of Florida, Neil is Airmaster Plus certified, has completed the Compressed Air Challenge curriculum, and is a Master Certified Systems Specialist through Kaeser's Factory Training Program. So, Neil, welcome to today's event. And with that, I'm going to pass things along to you to get us started. So, Neil, go right ahead.
Thank you, and welcome to today's webinar, Master Controllers, your compressed air systems watchdog. The U.S. Department of Energy conducted a survey and determined that for a typical industrial facility, approximately 10% of the electricity consumed is for generating compressed air. For some facilities, this is as high as 30%. Compressed air is often a critical part of production, and without compressed air, the plant may not be able to operate. So, not only is compressed air expensive to produce, but it can also be very expensive for plants when their compressed air system is offline for any reason. If compressed air is that expensive to generate and that critical, shouldn't it be carefully managed? Better yet, wouldn't it be best to have someone or something watching and monitoring it continually to ensure energy efficiency? Today we'll talk about the problems that can happen when a typical compressed air system isn't properly controlled. We'll also talk about the benefits of a properly controlled system, as well as how a master controller functions, how a master controller can impact system design, and finally, system design parameters you should be aware of. In a typical plant, there are multiple units feeding the compressed air system. This can be a significant advantage, as with multiple compressors, there is the possibility for redundancy. If one compressor is offline, then a second or a third, and so on, can run to at least keep the plant in a productive mode. With only one compressor, if that unit is offline for any reason, the whole plant could be shut down. The disadvantage of having multiple compressors operating the facility is how well are they operating together? Each compressor will have an individual controller or logic regarding its own operation, safety, startup, etc. However, how do these individual compressors talk to one another or play well with one another? On top of having multiple compressors supplying the flow, most systems don't have a steady airflow demand. Here's a typical example. This graphic doesn't necessarily mean the compressors aren't operating the system efficiently, but when you have various demands on varying shifts, how do you make sure that the most efficient compressors are actually operating? Without the advent of a master controller, there tends to be uncontrolled compressors cycling, trying to meet these demands, which then creates excessive wear and tear on those particular units. In addition, this leads to unnecessary pressure drop in the system, which can further affect production. Let's take a look at how a master controller affects a sample system. In this case, we've got two fixed-speed compressors, which are load-no-load compressors with a time-stop feature, which they're different horsepower as well. So these are compressors A and B, which you see off to the left a little bit. Compressor C is a variable speed, also called a variable frequency controlled compressor. Their individual flow profiles are shown on that left-hand side graphic. So they are all running independently of one another based on the input from the master controller. When we combined all three compressor flows in the middle graphic, we see how the master controller chooses which compressor to run. This is actually based on the operating pressure in the dry storage receiver, which is the third graphic called storage vessel. In most cases, a master controller will be adaptive and load and unload compressors based on activity in the facility, which affects operating pressure at this dry tank. Taken together, we get the total demand, which is the last graphic on the right. Notice the relatively stable operating pressure at the storage vessel graphic, but the varying flow profile in the total demand graphic. So that's what we would expect with a master controller. Stable operating pressure with a fluctuating demand, and all the machines operating very efficiently. We've talked a little bit about varying demand, as well as a breakdown of system operation with a master controller, but to really appreciate where we've come now in 2018, we should really look at where we've been. Prior to master controllers, and even today without a master controller, cascading pressure bands with multiple compressors is still an accepted practice. The end goal of cascading pressure bands is to ensure that all of the compressors don't load up or start at the same time. If that happens, your plant could have a huge demand spike or charge on your energy bill each month. By introducing a sequencer to cascade your compressors, it can regularly change which compressor is first on, last on, etc. So therefore, you can start to balance the load hours. In the end, because of this larger pressure band, this allows the baseline compressor to run at an elevated pressure, which increases overall energy costs, which we'll get to in a little bit. Notice that the overall pressure is almost a 15 psi swing. And this is just at the control point. And it could be even larger downstream in your facility. And really a 15-pound band with 4 compressors is probably a little bit light. I would expect to see that maybe more like 20, maybe even 25. Also note that the red line at the bottom represents the minimum acceptable pressure in the plant. So we don't want to hit that, otherwise we might not be able to meet productive demands. So we've identified the benefits from a cascade control. Compressors load individually and not all at once, as well as the detriments, higher operating pressure than necessary. With the advent of a sequencer and a control via external set points, the compressed air system can maintain a smaller pressure band than just a cascade control, and that's what we're seeing in the blue to the right. The average pressure comes down, lowering overall energy costs, which is a good thing. We're higher than the red line, that minimum required plant pressure, so there's still some room to drop the plant pressure a little further. However, just based on timers, we still need some buffer to ensure we don't fall below that red line. As external controllers progress, target pressure is introduced, and the set points are now based on that target pressure. Notice how the pressure band is smaller, what we see now in the green graphic at the right, than the blue area as well as the brown area on the left. And the average pressure is now significantly lower. But still, we have some room above that red line as a buffer, hedging our bets against low pressure. With the advent of adaptive pressure regulation, the average pressure is further reduced, and we are now as close as reasonable to the minimum required pressure, also referred to as P alarm in the graphic above for the plant. So that's what you see at the right-hand side that we've added. You can also see that there is some fluctuation in pressure. Rather than the tighter bands we saw in the green area, this pressure band can fluctuate. With these type of master controllers with adaptive pressure regulation, the master is looking to, number one, meet the fluctuating demands while maintaining critical pressure, but also, two, obtain the maximum efficiency of the system. In some cases, during low production periods, it can be more efficient to allow the pressure band to widen. So that's what we see at the right-hand side where the pressure comes all the way up, thereby cycling those compressors on the off shift a lot less than it would be to maintain a lower plant pressure. So there's a benefit between pressure and also cycling, which we'll talk about a little further. So far, we've discussed the first two items, improved pressure stability and also increased system efficiency. If you can recall the slide with the two children screaming at each other, then you'll understand the reduced maintenance cost and enhanced preventative maintenance topics. Additionally, the benefits for a master controller include minimized waste as well as the master controller's IoT capabilities. So let's break it down a little further for each of these points. Remember, we looked at cascade pressure control, which had as high as a 15-pound pressure band, and if you'll remember, I said it could even be higher depending on how many machines you have. Many pieces of equipment require a stable operating pressure at the point of use, and this can be accomplished via local filter regulator and lubricators, also known as FRLs. However, if these lines aren't regulated and pressure is too high or too low for a particular piece of equipment, the product quality could suffer, or this could increase product scrap. Further, maintaining a lower, stable operating pressure reduces compressed air waste, which we'll talk about on the next slide. In most compressed air seminars, you'll hear a reference to the Department of Energy's review of compressed air systems. Specifically, 45 to 60% of all compressed air generated is used for production, but the remainder is wasted energy. So how do you curtail these items, these wasted energy items? By reducing plant pressure. That's the easiest way to do it. This can be accomplished with a master controller. The major factors of waste are artificial demand and leaks, which are directly affected by pressure. Inefficient uses or inappropriate uses is not affected by pressure, so that's the other factor of waste. By reducing plant pressure, the amount of air being used is going to be reduced. At elevated pressures, all your demands are going to use more air, so leaks are going to leak more at higher pressures than they are at lower pressures. Drop the pressure, and your leak will leak less. That's artificial demand. We'll talk a little bit more about the monitoring functionality of a master controller later, but monitoring flows over time can also help you get a handle on your plant's leak rate. Finally, a master controller can reduce system efficiency, which thereby reduces wasted energy in your plant. I said reduce system efficiency, but it's more like improve your system efficiency, so less waste. Okay, if you've purchased a compressor, you might have heard that over 70% of the life cycle cost of a compressor is going to be energy. The balance, which is purchase price and maintenance costs, those are evenly split. Understandably, you'd choose the most efficient compressor, but what if you had older compressors in your system? How can you maximize system efficiency? A master controller should minimize the number of cycling compressors in your system. Typically, there should only be one of these compressors. This allows for other larger compressors to run fully loaded for longer, maximizing your compressor duty cycle. Ideally, baseload compressors should have close to 100% duty cycle, meaning there is little to no time spent idling, which would be producing no compressed air to the plant, but your motor is actually running. Further, as hinted in the last slide, reducing plant pressure to the lowest point possible will not only reduce your artificial demands, but also reduce the compressor generation pressure, which reduces overall energy cost. So one of the rules of thumb that we like to talk about in the industry is for every 2 psi pressure drop, it's equivalent to a 1% energy reduction. This is also the case if you say 1 psi is worth 0.5% in your energy cost. Predictive maintenance based on algorithms are starting to become more and more available. And as you can see in the graphic, the blue line continues to trend up. This blue line is the air end discharge temperature of a compressor. Notice that the flow, which is the black line, which is cycling up and down there near the blue line, isn't changing, let's say, significantly, but the blue line continues to trend up even while the ambient temperature, which is the green at the bottom, is within a certain range. Internal compressor controllers have enhanced capabilities, but we're asking them to do more and more with each new iteration of compressors. A master controller should have the adaptive pressure control like we discussed previously, but in the near future could have the ability to note potential service issues based on real-time data like we're seeing here. This is one of my favorite slides. I'm often asked, what's the most important data point to measure in a compressed air system? Well, most of us aren't measuring anything. And when there's a problem in the system, we'll address it immediately. So we're reactive rather than preventative, like we talked about in the last slide. So how do we become preventative? We've got to measure the system and interpret that data. These are just some of the items that I'd recommend monitoring. Alarms, general compressor operation, system pressure, and that's just system data. What we found is the reporting feature from a master controller showing system efficiency and system operation. Those are really powerful tools for plant engineers and plant managers to associate compressed air to your cost of production. Without a master, we can have multiple compressors fighting each other, loading and unloading, often based on other compressors' operation, so machines fighting each other. This increases maintenance costs of all your compressors. Plus, without a master, you can have additional compressors online for no reason, simply idling. We talked about that a little before. This is going to increase your maintenance costs because maintenance costs are based on service hours. Introducing a master to the system can balance the service hours on like-sized compressors, which can allow your compressors to be put on the same service schedule or just online, to eliminate machines that are online when unnecessary. So that's a big boon and can save trip charges as well. We've covered the benefits of master controllers at length, but one item that factors significantly in how efficient a facility can operate is how that system is designed. For the purpose of our comparison, we need to weigh what's important. And of course, this is going to be different for each plant, and it could be different for each procurement. Over a number of years, what's important on this list may not be most important the next time, or so on. I have here purchase price, and while this is an understandable consideration, I would strongly caution you not to let this be the only factor in your decision-making process. More often than not, the cheapest system up front ends up costing more over the lifetime of the system, and we'll get into that in a little bit, which is anywhere from 5 to 10 years. And I've been in the compressed air industry, about 14 years now, and I continue to see equipment that's been installed for 10, 15, 20, even 30 years. So, those lifetimes are different depending on what your considerations are. Also, if that solution offers you no redundancy and you can't afford downtime, then it could cost you dearly if there's any kind of repair. So those are things that you need to look at when you're designing a system or redesigning. Here we've broken down the cost between initial costs and operating cost. With initial costs, equipment costs, our purchase price, installation costs, as well as the size of the compressor room and the locations of the compressor room to already established utilities, these can heavily impact the decision-making process. With operating costs, these are a function of how the compressors are actually used. So specifically energy costs. So are they fully loaded all the time? What's their duty cycle? How efficiently do they actually run at the specific production levels? Also, what are the maintenance costs? So how do you compare various systems? And then what's the best way to design a system? Let's first look at an installation with a single compressor. Many facilities consider one compressor for operation, and that's still common today for sure. In this example, we're talking about a single fixed speed compressor, and that's going to have a lower capital cost when compared with a single variable speed driven or VSD compressor. These are often referred to as variable frequency drive compressor, just depends on the manufacturer. Single compressor installations are typically the lowest capital cost when compared with multiple compressor installations, and that's pretty advantageous, especially when you're working within a budget. However, one thing that always comes up in any system design is the cost of backup or redundancy. In everyday life, we say, don't put all your eggs in one basket. I know it's cliche, but it's the same with your compressed air system. In most cases, 2 eggs are going to be better than one in case one breaks or breaks down, in our case. With a single system design, the cost of backup compressor is equal to that single compressor. So those are the things that you have to think about. If your compressor is $50,000 and you want to have a backup, then you have another $50,000 procurement to do. But if you had a split system, it would be less. Further, comparing a single fixed speed compressor to a single VSD compressor, the VSD compressor is going to have a higher overall purchase price. With most things, it all comes down to pros and cons. On the pro side of a single compressor install, you'll have simple installation, small footprint, one power connection, one pipe connection, and a simple operation with a single pressure band. On the con side, what happens when a single compressor isn't operational? Absolutely nothing. The plant won't be able to run. Zero redundancy is a huge issue. Often, the lost opportunity cost due to downtime over 1 year could easily exceed the capital cost of a second compressor. Single compressors are more affected by changes in system demand, especially at low demand levels where the compressor is much less efficient. So if there's changes in your production seasonally, or if there's an economic downturn or something like that, you're going to see the effects of efficiency pretty much immediately. Should there be frequent cycling of the compressor due to that low duty cycle, this can also reduce your compressor's lifetime. Even single VSDs, which can operate between 25 to 100% fairly efficiently in your demand profile, they're not going to be as efficient at that lower end or even at the higher end because you're paying additional power to feed the drive as their multiple compressor counterparts. So those are things that you want to think about as well. A simple alternative to the single compressor station is to consider 2 fixed speed compressors, each rated for 50% of the demand. Notice the pressure band increases slightly so that we could cascade the units, so both units aren't loading and unloading together. Remember that graphic that we looked at originally with the pressure bands? This can be accomplished a multitude of ways, either via pressure settings on each machine to master-slave between the 2 compressors, or via a master controller. Again, what you see there with the master, you can get down to probably about 7 psi. While the capital cost for a multiple compressor system is going to be higher than a single compressor, instead of adding 100% compressor for that redundancy, we can consider a third 50% compressor as backup. So overall, that purchase price could come down. Therefore, again, redundancy is going to be a lower capital cost to add. The big benefits of the multi-fixed speed compressors is, again, that lower cost of adding redundancy. This is also providing better efficiency at lower demands than a single fixed speed compressor. And you'll see that in some graphics later on as we get to it. And depending on the control range of the single variable speed drive compressor, could have a comparable efficiency at those lower demands as well. Maintenance intervals, again, are traditionally based on service hours of the compressors. Therefore, if we have multiple smaller fixed speed units, we can stretch out the operation, balancing the service hours between all the compressors. This typically results in more predictable service intervals with all 3 compressors, or as many as you have there, coming due at the same time, saving multiple trips. Like we already talked about with a master controller, balancing service hours can go a long way with saving the plant in maintenance costs. The multiple fixed speed compressor installation will typically require more physical space at your facility. It'll need more utilities, power, water, etc., if you have water-cooled machines, and infrastructure, piping. With more compressors, the overall project will typically cost more. This scenario also has a higher potential pressure band, again, due to that cascading of the compressors. Our example was 15 pounds. But if you're using a master, we can in effect reduce that pressure band, and also this will help balance the load hours of the unit. Big benefits for a small increase in capital cost by adding a master controller here. Lastly, we'll look at a split system with a variable speed drive compressor. This is representing about 60% of the overall demand, and it also has a smaller fixed speed compressor, which is representing about 40% of the overall demand. The pressure range is again about 15 psi to ensure that both compressors aren't loading and unloading together, which of course would defeat the purpose of having multiple compressors handling the demand. This is going to require a slightly larger fixed speed compressor as a backup, so redundancy, hence the medium redundancy cost designation. You'll also be looking at a medium installation cost designation, as variable speed compressors are, again, more expensive than their fixed speed counterparts. By adding a master controller here, you can further reduce that pressure band. And additionally, a master controller will ensure that the VSD always runs as the trim, and that the most efficient compressor or combination thereof will be operating at any given time. So again, a great opportunity for a master controller there. The goal of any system design is to maintain the best possible efficiency over the entire demand range. We often see where facilities scale up or down, and often this change could happen quickly without the ability to procure new compressors. Those facilities that size in this kind of stepwise design or a split system design, as we show here, or call it out here, are able to maintain their efficiency levels very closely regardless of the demand, especially when they already have a master controller. One large variable frequency drive can have a huge control range, but at those lower flows, the efficiency level is definitely reduced. If the single variable speed, variable frequency drive compressor spends significant time at that low level, the benefits or energy savings could be significantly reduced, and you could see increased maintenance costs and possibly unexpected downtime, as well as shorter lifetimes of your variable speed unit. Additionally, systems with a master controller can provide necessary monitoring and reporting. Remember that IoT that we just talked about, as well as they're going to operate your station as efficiently as your design is going to allow, therefore reducing your energy costs, waste, and stabilizing your operating pressure. So we'll spend a little time discussing control range on the next slide, but when using the split system design, sizing the VFD, VSD compressor at 60% of the demand and the fixed speed compressor at about 40% of the demand will fit within the VSD's control range. So we'll talk about control range here. In this example, we take 1,450 CFM VSD compressor. It's got a minimum flow of 62 CFM, which is only a 43% turn down. So, it varies based on the machine, how far you can go. In a lot of cases, you're down to 22, 25%. In this case, it's only 43. Below 625 CFM, the VSD compressor is going to run load and unload, which will be less efficient, and it's going to generate a fluctuating pressure, which you shouldn't see with a VSD in the first place. Also, if there was a same size fixed speed compressor, again 1,450 CFM in the plant, what happens when the plant needs more air than the VFD or VSD can supply? So if we needed 1,451 CFM, but we're only supplying 1,450 CFM. Well, that same size fixed speed compressor is going to have to load. So you'll have another 1,450 CFM online for just one additional CFM. So you're increasing your supply significantly. So the system is going to hit the unload pressure of both machines typically really quickly. Usually in this scenario, we see both the VSD ramp up and down at the same time the fixed speed compressor is loading and unloading. This can occur all the way until the demand exceeds the VSD's minimum speed, in this case 625 CFM, plus the fixed speed's rated output, which is that 1,450 CFM. So anywhere above 2,075 CFM, system stable, pressure stable, the compressors aren't ramping up and down rapidly and fighting each other. If the plant never runs below 625 CFM, or if it always runs between 1,451 CFM and 2,075 CFM, then we've got no problems. However, if the plant is in the area too long in these scenarios, it'll not only be efficient, but again, it can cause service-related issues for the compressors. A split system design will typically be the most efficient at all demands, and it can provide for redundancy should the VSD be offline for any reason. It's typically going to be a lower capital cost than a single VSD system as well, just based on horsepower. Alternatively, the split system design will have a higher capital cost than any 100% fixed speed compressor, or perhaps the multi-unit fixed speed compressors. And the cost of backup here with the split system design, which let's say cost of redundancy, is going to be higher than a multi-unit fixed speed compressor, but lower than that single VSD. Now that we've talked about the pros and cons of various station designs, let's talk about how multiple compressor systems can be even more efficient. These are items that we've already discussed, but we'll highlight them once more. We've mentioned the cascade pressure band. This is going to result in higher pressures, higher average pressures really, and that's going to result in higher operating costs. Remember, 1 psi is equal to about 0.5% more input power. This is also going to result in higher artificial demands. So your leaks are going to leak more at higher pressures, your tools are going to use more air at higher pressures. Roughly translated, 1 psi is equal to about a 1% increase in demand of all unregulated uses. Not only that, but remember that control range discussion with the same size VSD and fixed speed compressors? This typically happens with multiple compressor rooms that lack any external controls. The compressor internal controls, they're going to drift over time, and the units start to load and unload much closer than intended, and you may now have two compressors cycling in two different rooms versus just one. So obviously not what you'd want. That's going to significantly increase the power consumption and will also affect the lifetime of the compressors from a wear and tear standpoint. Additionally, if there are multiple modulating compressors, we often see all these units throttled back, consuming significantly higher power than necessary, as many of them could really just be turned off. Flow controllers are a useful tool in the field to drop the network pressure to the lowest possible level. By doing so, this is going to address the artificial demand issue, because now you're regulating to the distribution piping if you have unregulated uses. So instead of having 110 psi, you might have 90 psi or 80 psi, because the flow controller is going to regulate pressure to that distribution piping. In systems where there are or were multiple modulating compressors, a flow controller was a great way to reduce overall energy consumption. However, often the generation pressure, which is at the compressor discharge, must remain at a higher level to create needed buffer for the flow controller to actually work. Typically, that's about 5 to 10% of the inlet pressure. The flow controller doesn't control the compressors at all, only that downstream pressure. So we aren't capitalizing on improved energy efficiency of the compressors. Now, there are cases where a flow controller can work really well with that needed storage buffer. So if you have high intermittent demand events and they're going to take the entire system down, or necessarily speaking are going to turn on a third or fourth or fifth compressor, by having a large storage volume and operating at a higher pressure, and then using the flow controller to deplete that storage volume, you can, in effect, keep off that third or fourth or fifth compressor, which can really save you significantly on your demand charges. However, you're still going to pay for the generation charges to create that storage volume. With a cascade pressure already established for our three examples and the needed reserve buffer in a storage receiver, plus a little bit of differential for the flow controller itself of at least 2 to 3 psi, which is going to be varying by manufacturer, we have a total differential pressure from the compressor discharge to after the flow controller of between 17 and 28 psi. Wow, just incredible to look at that number. That's a very large pressure swing to consider. So is the downstream pressure set point of the flow controller low enough that we can effectively run the flow controller and not overpressurize the compressor? So that's a big question. So what addresses some of the misgivings of flow controllers? And before we move on, I'd like to say that there are some really good applications for flow controllers. If you're trying to build a buffer, keep some of your machines offline until you have a big demand event, then a flow controller can be a great thing. And like we say here, if you can handle the larger pressure band and the larger generation pressures, maybe keeping compressors off is the way to go. But in most cases, we won't see that. So as discussed before, a master controller can address some of these issues, and it's going to be able to coordinate all your compressors within the system. Newer master controllers on the market are based on algorithms that consider rate of change calculations versus simple pressure band controls. So it's learning the stations and making simulations for the most efficient operation. When a master controller is installed and there are multiple smaller compressors, efficiency can be optimized, resulting in lower operating costs. Master controllers also can be accessible remotely and stream data and message to plant operators in real time, which brings us back to that IoT or Industry 4.0. When compared to flow controllers, they're generally more expensive and can have significant installation costs. And they don't have explicit reserve capacity like a flow controller creates. So those are some pros and cons and comparisons. However, rather than that total of, remember what we showed, 17 to 28 psi possible, a master controller is typically going to work with a 3 to 7 psi range, and that can vary depending on what machines you have, depending on how much storage you have, and so on. Could be larger than 3 to 7. Again, it depends on, increasing the pressure. Remember, anytime we're increasing the pressure, we're increasing the generation cost. So every 1 psi is equal to 0.5% in energy increase or likewise decrease. So it's better to supply your airflow at the lowest possible pressure, which is going to allow your compressors to turn off and shut down, saving energy. So you're going to see that with your master controller by managing your machines. The other large benefit of a master controller is having everything on one pressure band so that you're not fighting one another. So that's how we're able to accomplish that 3 to 7 psi. Getting back to the sample systems we talked about, remember, single VFD, single fixed, multiple fixed speed units, and then the split solution, 60%, 40% VFD to fixed. We're going to give some real-life examples here with one 250 horsepower VFD, one 250 horsepower dual control or fixed speed machine, which is a load-on-load compressor with a time-stop feature, and then two 125 horsepower dual control or fixed speed compressors. So we'll refer to that as a split solution, as well as one 125 horsepower VFD and one 100 horsepower dual control or fixed speed, again, referred to as a split solution. So how do they compare efficiency-wise over the course of a typical demand profile? This graphic shows specific flow or system flow, at the bottom right, so ACFM versus specific power, or kilowatt per 100 CFM, which is an efficiency marker or a key performance index of your compressed air station. So if you've ever seen a KGI data sheet, Compressed Air and Gas Institute, we rate all of our compressors at 100% duty cycle for dual control. For variable speed and variable capacity machines, you have multiple data points over the course of their range. But for load-on-load dual control machines, you have 100% power consumption, and that's a kilowatt per 100 CFM. So what happens if it's lower? So in this graphic, we're going to show a flow range of 200 CFM through 900 CFM, which is about 20% to 90% of our total demand. So we're starting out with about 1,000 CFM. Starting from the top of the graphic, the dual control compressor, or our fixed speed, our one 250 horsepower fixed speed option, that's the orange line. The single fixed speed option is extremely inefficient, even with ample storage volumes at 60% and below, so 600 CFM and below, when compared with pretty much any other station on this graphic. So remember, we talked about budgetary numbers. Budget was really important. We want one machine. That's the only thing that we have. It's the only thing we have available. Well, if you run really 60% or below, you could be really wasting energy. Not only that, but it's an application-related issue, and you can have service issues down the road. So that lifetime that we talked about, is it 10 years? Is it 5 years? You're probably looking at a lower lifetime as well. But at the higher level, so if your single machine is going to run at those higher levels, anywhere above 600, the single fixed speed compressor is becoming more efficient. The split solution, which is our two 125 horsepower fixed speed compressors, that's much more efficient at our lower demand levels, and it's a little less efficient at the higher end. So it depends on what your averages are or what your plan is actually doing as to which is best. Whereas both options with the VFD are really the most efficient, with the split VFD fixed speed units slightly more efficient throughout the range. So that's that yellow line at the bottom. Here's a table that compares each of our 4 options that we've been discussing with various design parameters. So the design parameters on the left, called system design, that's the column that we're looking at. The table gives a red, yellow, or green based on which system or option is best at each design parameter. So we've got 4 options here. So we've got a few reds, a green, and a yellow in each. Green's going to be the best, and red's going to be the worst. So, like traffic signals, red means stop, green means go, yellow means, well, it depends on, where you are. So for example, with the single compressors, VFD or fixed, the redundancy design parameter is red, meaning there's no backup in the system. Whereas it's green for option 3, which are our 2 fixed, and yellow for option 4, which is that VFD fixed speed system, meaning option 3 has the most redundancy built in, but option 4 has some as well. So, that's a good thing. Overall, a single fixed speed unit has more red than any other option. So that comes in with 8 reds of our total 10 design parameters shown here. The single VFD and the 2 fixed follow behind with 5 overall each. Again, we've shown which systems are most beneficial based on which design parameter, but the importance is going to vary based on each plant, and like I said, that could change over time. The main items to consider when procuring a new compressed air system, as outlined in this presentation, are efficiency, capital, reliability, and footprint. We looked at the efficiency graphic on the previous slides. Single fixed speed, generally speaking, least favorable over the whole range. The multi-unit fixed, much more efficient, but not necessarily at the higher end. And with the 2 VSD options, those are the most efficient. That capital difference could be higher than the 10% shown here. The VSD options are always going to be more expensive, but the more units installed, the higher the installation costs and also the larger footprint. Again, redundancy is also something to consider, and all your eggs in one basket means when that unit's down, no work's possible. Whereas with those split systems, we have an opportunity to at least meet some production. Also, you consider the ROI between each of your options. Notice reliability. VSDs are pervasive now in the industry, and many facilities are dusty and dirty environments which can really adversely affect the drive, meaning a catastrophic failure. Also, bad power can have a more prevalent effect on a VSD than a fixed speed unit. Therefore, these ancillary issues can also affect the decision on whether to install a VSD unit. either in a single or in a multi-unit application. Is there a right answer? Honestly, it's going to be or it'll vary based on each use case. And in the end, all manufacturers can provide multi-compressor solutions with a master controller, and they should. As mentioned earlier, many facilities only consider capital cost, and if the capital cost only allows for one compressor, then that's the answer. Again, this is going to traditionally be less efficient, especially for varying demands, especially with demands that are less than 60% of that unit's capability, really than any other station that we considered. And this is going to lead to a lower lifetime of the equipment based on constant cycling. And most systems don't have sufficient storage in the compressor room either, so that'll also take its effect. So really don't assume anything. Find out. How do you find out? Well, take a demand profile of your system through a compressed air audit, or trend the data that you're already recording and design your system, or tweak your system based on this information and any perceived changes expected throughout the lifetime of your equipment. Planning for tomorrow, today, can set your facility up for continued success. This really can be easily done with a master controller if the master controller is already installed in your system. So this concludes our session today, and I want to thank everyone for listening out there. For more information, please visit the website link shown herein, and we look forward to your questions.
Okay, thanks, Neil. And now we'll get to the Q&A. Okay, our first question is, does a master controller help with leaks?
Thanks, Kim. In general, master controller is going to be able to visualize what's going on in your system. So, leaks are going to happen all the time, but what you're really going to notice on the off shifts, either nights, weekends, holidays, what the flow values are. So master controller is going to figure out what's going on with your compressors, maintain operation of those things, as well as should be data logging flows, pressures, and other information on your system. So you can dial in really remotely from even your cell phone these days and figure out what's going on during those off shifts. That gives you an idea on what your leak load is. So, if let's say your total flow is 1,000 CFM, and then the leak load or the off shift load is 500, that equates to a 50% of the overall demand. So that would be something I'd say, okay, yeah, let's dial this in a little bit and figure out where those leaks particularly are. So in general, a master controller is really just going to help with the visualization of what's going on in your system on a day-to-day basis, and can really give you some inherent clues on how you can improve your efficiency.
Okay, great. Thanks for that. Another question's come in. Why are cascade pressure bands inefficient?
Sure. We had a graphic earlier about kind of the history of master controllers, and we started with the cascade pressure band. Cascade pressure band was great many, many years ago, and even today we still see that practice used when folks don't have a master, or perhaps it's just not part of the budgetary concerns this particular quarter or when they buy new equipment. But it's a great way to ensure that not all your equipment starts and stops at the same time, or loads and unloads at the same time. So, from a certain standpoint, when you do have cascade pressure bands, you're going to run at an elevated pressure when you're on your low demand shift. That elevated pressure is going to increase your artificial demands. It's going to make your leaks leak more, and that is going to create additional costs. It's also more costly to run at a higher pressure. The generation, the power required to meet those higher pressures is higher as well. So there's your inefficiencies. And then, when you look at trying to dial down to the lowest possible pressure of your system, it's awfully hard to get there when you're cascading. So master controller, what we showed in the slide, will get you down to really the lowest possible pressure that the plant requires. And in that way, you're going to save on the generation, you're going to save on that artificial demand and your leaks. So it's really a a double-edged sword, which is in your benefit. Good question.
Okay, thanks. Moving on to the next question. How would a system with multiple compressors have lower maintenance costs than a single compressor?
Sure. It may not make a whole lot of sense if I have 3 machines or one, which is going to have the most service costs. But if, let's just say, for an easy example, that your operating hours per year are 6,000, and you have one larger variable frequency drive compressor, that single machine is going to have 6,000 hours every year. And so you're going to have to do a minor and a major service and maybe more for that particular unit. But if you had, let's say, a master controller and 3 machines, for example, each of those compressors would have 2,000 hours of runtime, assuming that they would be able to handle the demand. And in that case, you'd have a lot less service for those machines per year, and maybe you wouldn't quite get to that major PM. And also, those machines are going to be smaller, so the maintenance costs of those pieces, filters, and so on, internal to the machine, probably going to cost a little bit less as well. So that's one way you can see lower maintenance costs. Plus, what I mentioned in the webinar too, if you have multiple machines, let's say you had the single VFD and you wanted to have a backup, well, backup may not have run, but in this case, you would have awkward service hours with either of those 2 machines. With machines that are, let's say, like-sized or have the same amount of hours, you can try to get them via the master controller to have the same service intervals. So then you're saving some trip charges as well.
Okay, thanks again for that. Another question here. At what percentage of its total capacity does a VFD compressor run less overall efficiently than a fixed-speed compressor running at 100% load?
Okay, so that's a good question. So fixed-speed compressor running at 100% load is always going to be the most efficient machine that's going to be out there when you're comparing with a VFD if they're the same size. And you'd have to really look at a KGI data sheet to confirm that. But let's say it's 100 horsepower VFD versus 100 horsepower fixed speed. If they're both running fully loaded, then you have to feed the VFD drive 3 to 5% extra power. So that's where you're going to get a discrepancy. Now, when you start dialing back on the VFD, that's where the VFD starts to become more efficient. And then with, let's say, a fixed-speed compressor, which, let's just call it a dual control machine, storage is going to make a big difference in how the machine performs. So, at 50% duty cycle, that's usually where it's going to be least efficient from a fixed-speed compressor. That's especially true if you don't have enough storage. So if you have a 1 gallon per CFM storage ratio for your fixed-speed dual control compressor, that's really the worst place you could ever run it. So certainly the VFD is going to be a lot more efficient during that period. If you have a significant amount of storage, then the VFD and the dual control are going to be similar, but not necessarily quite. So usually what we say is the VFD is most efficient between the operating parameters of 40% and 85%. So that necessarily means, okay, well, what am I actually going to run at? So, when you look at a single fixed speed versus a single VFD, typically your efficiency levels are going to be better with your VFD across the range. But if you split that system like we showed in some of those charts, you can really start to gain efficiency with fixed speed solutions against the VFD, especially when you add the master and you're running more so at that lower end, that 40% or lower. That's where you can start to gain some efficiencies. Good question.
Okay, we have a question from the audience here. How can I tell if my compressors are not properly controlled?
Okay, yeah, that's a great question. It kind of reminds me of when I turn my back on my 3 kids at home, and then it starts to get louder and louder and louder. And then you turn around and you're like, okay, well, what exactly just happened? And it's the same thing in a compressor room. If you're not walking into the compressor room, then you're not getting I'd say you're getting real-time data. Maybe you're getting this off the cloud. Maybe you're looking at your master controller screen, but you're not walking into your compressor room. You may be missing something. Usually when you walk into a compressor room, you can hear it. You can see the machines. You might look at the operating conditions. You might look at your overall duty cycle on the units and say, okay, well, yeah, I would expect maybe a couple 100% duty cycles on these, and I've got one that's a trim. Maybe that's going to be 50%. Duty cycle is really a key index for me that I would look at and say, okay, if the duty cycles are close to 100%, then I'm doing a great job. But if they're not, then yeah, that would definitely be an indicator to me that I can improve in efficiency. Or if I look at one number and I look at flow, and the flow says average flow for the system is 500 CFM, but I walk into the compressor room and I've got 3 machines running, that may not equate. So there's a lot of different things you could look at to figure out if you're running inefficiently. Those are specifics, but also specific power. If you're monitoring your system and your specific power is, it depends on what your operating pressure is, but I'd say if it's, over 18, 19, 20, it's somewhere above that range, and I'd say, yeah, there's definitely some improvements that can be done.
Okay, great. Looks like we have time for one more question, Neil. Should my backup compressor be connected to the master controller?
The intro we wrote, I've seen thousands of audits, and one of the big things that what comes up is, oh, well, that machine never runs, and traditionally that is an untruth. So, in my personal opinion, I would do everything I could to get the backup compressor on there because, in a lot of cases, what the master controller can do is just activate that particular compressor 1 or 2 hours a week. Number one, make sure that it's a reliable compressor, and then number two, it gets the oil flowing, it gets things moving, and you're ensured that it's going to start up the next time when you really need it. So, and then you can get that visual feedback if your master controller has, a web address that you can dial into and make sure that it's actually running. So, yeah, I would definitely recommend it. And, from a certain standpoint, if you've got a 20-year-old compressor that's a backup and you've got, 2 or 3-year-old compressors, it's probably time to replace that backup and then just have the master controller rotate through a backup so that your reliability is ensured all the time.
Okay, lots of good information there. We're going to be wrapping up the webinar right there. Thank you again to our presenter and for spending some time with us today. And thank you to all of our audience members for being a part of this webinar event. Take care, and we'll talk with you soon.